Thanks very much, Guo.
Okay. So first, I want to thank the organizer for their kind invitation. It is nice. It is my pleasure to have the chance to speak here. Now I'm going to share my screen. So can anyone see my screen?
Yes, it's working.
Okay. So today I'm going to talk about exponential asymptotics in particle chains. This is the discussion section. If you have questions, please feel free to stop me. And this is a joint work with Chris Lustri and Mason Porter. So this is the outline of my talk. First, I will give a general introduction to granular chain. Then I will introduce how we apply exponential asymptotics to perturbed granular chain. In the end, we are going to discuss the exponential asymptotics with different leading order solutions. So here is a general picture of granular chain. A granular chain is composed of aligned spherical frictionless particles, and the interaction between them is given by power law, which is given by here. So the key information about the power law interaction are two. One is the larger the compression is, the larger the potential is. Secondly, it is this interaction potential is zero when the particle lose contact with each other. The physically most significant case is alpha equals 3/5, which corresponds to Hertzian interaction. And also this exponent actually is tunable. So it is also interesting to consider other values of alpha. And for our discussion, alpha is greater than 1. In fact, I actually have a toy model for the granular chain, like this. So here is the toy model of the granular chain. Once we have a granular chain, we can play with it. For example, so as we can see, the energy indeed propagates along the chain, because initially I excite one end, but the other end start moving. So the energy indeed propagates. So it is a natural question to address. Whether the energy travel as a localized bundle or whether the energy dispersed among the chain. Here, in fact, both are possible, and here are two possible forms of traveling waves in particle chains. In the left panel, the energy is dispersed everywhere in the chain, while in the right panel, the energy always stays as a localized bundle. So the localized traveling energy bundle is also known as oscillatory wave. And the existence of oscillatory wave in Hertz chain was first reported in this study. Later on, there is a rigorous mathematical proof showing that lattice with superquadratic potential admits oscillatory wave. So for chains with power law interaction, in order to support the propagation of oscillatory wave, we need the exponent to be greater than 1. Other than supporting the propagation of oscillatory wave, the granular chain is also highly tunable. Therefore, it is feasible to obtain perturbed chains by adding heterogeneity to a homogeneous chain. For example, we can get a chains with impurity, with random particles, or alternating masses. And in our study, we are going to focus on woodpile chains. So the woodpile chain is also a type of perturbed granular chain. So it is a system of orthogonally stacked slender cylinders. Along the direction of the stack, the interaction is given by the Hertz force. And in the perpendicular direction, the deformation is modeled by internal resonators. So this is the real woodpile chains. And in an idealized model, we can see it is we will have a monatomic Hertz chain. And in this chain, every particle is connected to an outside particle by a linear spring. And first, the woodpile chain is also can be obtained in experimental settings. And a recent study show the traveling wave in woodpile chains are typically Nanoptera. So this is the typical oscillatory wave where it is highly localized. And Nanoptera is not localized. It is composed of a central oscillatory wave and exponentially small tailing oscillations on one or both sides of the central wave. Our goal is to determine the behavior of this oscillation in the small mass ratio limit. Because the amplitude is exponentially small, so we need to apply exponential asymptotics. So here is the second part of today's talk. First, we are going to write woodpile chain, the governing equation for the woodpile chain. So this is the equation governing the particle inside the monatomic Hertz chain. And this is the governing equation for the particle outside. And eta is the mass ratio. For our study, we are interested in the mass ratio is small. In classical perturbation method, we are going to write the solution as a power series and solve the terms in the power series recursively. Doing this for nonlinear system can be very complicated. Also, since the oscillation is exponentially small, so the oscillation will be smaller than any term in the power series. So expanding as a power series cannot reveal the oscillation. As a result, we need to use the exponential asymptotics instead of classical asymptotics. First, we are going to see in the leading order, the system becomes the following equation, which is exactly the monatomic Hertz chain. So that's why the woodpile chain is indeed a singularly perturbed Hertz chain. Asymptotic power series in general is divergent. If we plot the difference between the exact solution and the approximated solution, as at the beginning, the more term we include, the smaller the error is. However, at some point, the error stopped to decrease. Instead, it increases. So if we truncate at the minimal error point, then the remainder is exponentially small. And also the minimal truncation point is asymptotically very large.
So sorry, I missed this, and I'm a bit afraid of not asking the question. But can you just remind us what the physical interpretation of U and V are?
Oh, sure. So U is the particle inside the monatomic Hertz chain, and V is the outside particle.
Okay.
So essentially, we have inside particle, outside particle. Outside particle is connected to the inside particle by a linear string.
Okay. And eta is some aspect ratio of their forces?
Eta is the mass ratio.
The mass, okay.
Is the mass ratio between these two particles.
Thank you.
Yeah, and we are interested in small mass ratio. So that is the mass outside is very small. So essentially is to truncate power series. Now we are writing the solution as the truncated series. And now we have a remainder term. If we are truncating at the minimal error point, the remainder term is exponentially small. During the exponential asymptotics, we need the leading order solution. We also need a form of the later order term. So we follow in the choice of this study, which writes UV as factorial over power. Gamma is known as the singularity function. It is 0 at the singularities of the leading order. Substituting this form back to the governing equation, we can determine the functional form of chi, u, v. We can determine everything. And then we can find the governing equation for the remainder term. Then writing the remainder term using the WKB. So it's exactly the same as WKB, except we are going to have a Stokes multiplier in front of the WKB, the classical WKB method. So when we are away from the Stokes curve, the multiplier takes a constant value. In the neighborhood of a Stokes curve, the Stokes multiplier varies rapidly. And we need to decide the jump in the Stokes multiplier. So the Stokes curve is very important to our analysis, and it is completely determined by the functional form of the singulant. It appears at the place where the real part, real chi is real and positive. So applying the exponential asymptotics, the first step is always to find the leading order solution. So the leading order solution is the solution to the leading order system, which is this system. It is nonlinear, non-integrable. So we don't have an explicit exact solution. As a result, we need to play some trick. Since this system has a linear limit, so we are going to assume the deformation is small, so we can expand the potential as a Taylor series, and then we take in the continuum limit. After taking the continuum limit, we are going to get the KdV equation. KdV equation has an exact solution. We are going to use the KdV equation to approximate the leading order solution of the Hertz chain. So once we obtain the KdV solution, then by doing integration, we can obtain the leading order solution of the woodpile system. That is a tanh function. After we obtain the leading order solution, we can know where the singularity of the chi is. So indeed, the tanh function contains the singularity given by this expression. And in the exponential asymptotic analysis, the singularity that are closest to the real axis contribute most. So hereafter, we only concentrate on the singularity that are closest to the real axis. So here is a general illustration of the Stokes curve. So we have two singularity, and they are connected by a Stokes curve. Then applying the exponential asymptotic analysis, we can obtain the tailing oscillation, which is given by this expression. And then we compare our prediction with numerics. And here is the comparison. So from our analysis, we can see the amplitude of the tailing oscillation is exponentially small in the eta, small parameter eta, which is directly related to the mass ratio between two masses. It is exponentially small and also is never zero. It's always there. This actually is contrast with a recent study, which shows for woodpile chains with zero pre-compression, which is a strongly nonlinear region. Because the study showed that in this system exists sets of parameters at which the tailing oscillation disappear. The disappear does not happen for us at all, because in our case, the oscillation are always present. Because in our study, we consider a weakly nonlinear case, our pre-compression is very large. And this study is for zero pre-compression. And for the zero pre-compression, there are sets of parameters which admits at which the tailing oscillation disappear and the Nanoptera becomes solitary wave. And the set of parameters also known as anti-resonance condition. And also our previous study showed that anti-resonance condition does not exist for woodpile chains with strong pre-compression. So next we are going to study the woodpile chains with zero pre-compression to see if we can find the anti-resonance condition at which the tailing oscillation disappear. So now the leading order system become this. This system is highly nonlinear. It does not have a linear limit. We can't expand around a parameter. So we can't deform it to the KdV equation anymore. Instead, we are going to apply an analytic numerical hybrid method, which is first proposed in this study. So essentially, we are going to assume the solution U takes a form of tangent. It takes this form, and the argument of tangent is a polynomial in Kasai. So we need to decide C1, C3, C5. And by taking the derivative of U0, we are going to obtain C1, taking the third derivative, we are going to obtain a combination of C1, C3, and so on and so forth. Then fifth derivative, we are going to get C1, C3, C5. So we can solve C1, C3, C5 recursively. And the quantity in blue is what we are going to obtain numerically. So we are going to numerically determine the first derivative, third derivative, fifth derivative, and then we are going to solve for the coefficients recursively. First is this approximation method indeed gives we can obtain a very nice agreement with the exact solution. And this table contains all the coefficients for different values of alpha, where alpha is the exponent of the interaction potential. And once we have all the coefficients, by solving this equation, we are going to obtain the singularities contained in the leading order solution. And now, in the weakly nonlinear case, we only have one singularity pair. However, for this case, for all the values of alpha, we are going to have two singularity pairs. As a result, we are going to get two Stokes curve. Each Stokes curve generates one set of oscillations. So the total oscillation is a superposition of these two sets of oscillations. So this is the general figure. So this is the undisturbed region. This is the region where only one oscillation turned on. This is where two oscillations, both are turned on. And these two sets of oscillation has the same amplitude but different phases. So by adjusting the system parameters, we can let the oscillation out of phase, so they can cancel with each other. So this corresponds to the anti-resonance condition. And here is the amplitude. Here is the total oscillations. So as we can see now, it is the multiplication of an exponential function and a trigonometric function. When the trigonometric function is 0, the tailing oscillation is 0. And here is the comparison between our results and the numerical simulation. So for all the values of alpha, as we can see, the anti-resonance condition, which corresponds to the dip, we have very precise prediction for the anti-resonance condition for all values of alpha. And the amplitude of the oscillation gets more precise as the value of alpha increases. So for alpha equals 1.5, we can see the error is still visible. When alpha equals 2, the agreement is really well. And for even larger values of alpha, it's pretty good. Then we analyze why the error is showed up. Why error showed up for relatively smaller values of alpha? Because in our calculation, we need to decide the coefficient, and the coefficient of C5 is directly related to the fifth derivative of U0. And the derivative is computed by numerics, and taking numerical differentiation can magnify inaccuracy. The accumulation of errors is significant for small values of C5, because for when alpha is small, the C5 is really small. When alpha gets bigger, C5 gets bigger. So we also include the simulation for alpha equals 1.2. So the value of C5 is even smaller, and the agreement is even worse than 1.5. And as C5 gets larger, then the agreements also become significantly better. So we have demonstrated that when the pre-compression is 0, there are two Stokes curves, so there exists anti-resonance condition. And when the pre-compression is very large, then there exists, then there is only one Stokes curve. So the oscillation can never be cancelled because there is nothing to interact with it. So there is no anti-resonance condition. Therefore, it is interesting to study the transition from the 0 pre-compression to large pre-compression. So next we are going to characterize the singularity behavior in the leading order solution as we increase the pre-compression and we fix the leading order amplitude. So as illustrated in the left panel, as we increase the pre-compression, the singularity pair in the leading order solution become closer and closer to each other. And at a certain point, it hits it coalesces, and the anti-resonance condition disappear at the critical value. So the critical value of the pre-compression is proportional to the amplitude of the leading order wave, as illustrated in the right panel. So this is the third part of my talk. Because the exponential asymptotic analysis need the explicit form of the leading order solution. For different leading order solution, the location of the singularity can be different. So the subsequent results can be different. So the third part is to study how the different leading order solution can affect the results of exponential asymptotic analysis. For this section, instead of considering a power law woodpile chain, we are going to consider a Toda woodpile chain. So what is the difference? The difference is previously the interaction is power law. Now we are going to have exponential interaction. Why we want to consider Toda woodpile chain? Because among many particle chains, Toda like this is among very few who has exact leading order solution. So we can apply the analysis on the leading order solution. Then we can compare our analysis with the exact leading order solution. So here is the exact leading order solution is given by a logarithm, is given by this form. And the kappa is the solidum parameter. The psi is the co-moving frame, and the solidum velocity is given by this expression. A profile of the leading order solution. So again, it is as a kink shape, like a tangent function. The amplitude is directly related to the solidum parameter, so it is 2 kappa. First, we are going to do exponential asymptotics with exact leading order solution. So first, we obtain the singularity pair. After we obtain the singularity pair, then we apply the exponential asymptotics. We obtain the amplitude of the oscillation. And we compare the amplitude of the oscillation with numerics. So as we can see, the agreement is very good. which means the exponential asymptotics is an effective method to characterize the amplitude of the tailing oscillation. Now, we will pretend we don't know the total lattice has the leading order solution. We will say now we have this lattice, we don't know it has a solution. So what we are going to do with this system? Well, this system also has the linear limit, so we can deforming it so we can expand the exponential, and then we deform the resulting equation into the KdV equation. Then we get a solution of a tangent function given by this expression. So this is now our leading order solution. And if we are using the exact solution, we are going to get two singularity pairs. And if we deform it into the KdV equation, now we only have one singularity pair given by here. And applying the exponential asymptotic analysis, we obtain the amplitude is given by this expression. So this amplitude never goes zero, different from the exact solution where it has the cancellation. And here is the comparison for kappa equals 0.25, 0.35. So like for so when the kappa is small, the first dip always show up around 1.15 here. And when kappa is small, the first dip is too small to be detected. So we can say this approximation is more or less close to the exact result. However, when kappa becomes bigger, then the first dip becomes detectable. We can see near the dip, the approximated result is not a good description of the of what we can see in the numerics, because clearly there is a dip, and the result with long wave approximation can never catch the dip because it only has one singularity pair. So now next we are going to consider the method which we applied for the Hertz chain with zero pre-compression. So we are going to fit it with a tangent function, because the total solidon, as we can see, it also has a kink shape like a tangent function. So we are going to fit it with the tangent function. Well, C1, C3, C5 will be derived as previously using numerical computation. So for kappa equals 2, we find the values for C1, C3. However, C5 become negative. So in general, we can't include the negative coefficient. The reason is the following: if we plot the displacement with only positive coefficient, we actually get a good agreement with the exact value. But what if we include a negative value? For large values, the negative sign actually forces this tangent function to switch direction. So we can only include to C3. So we have C1, C3. Now we are going to solve for singularities. And we obtain the singularity is given by this expression. And recall that this is the singularity from the exact solution. And the resulting amplitude is given by here. And this is the amplitude from the exact solution. So we can see the cosine part which is kind of close to each other, but because the imaginary part deviates from the exact solution. So our agreement is given by here. So the anti-resonance condition, our prediction on anti-resonance condition, where the dip is, actually is close to what predicts by the exact solution, but the amplitude deviates from the exact solution because the imaginary part of the singularity is different from the exact imaginary part. So is when two solutions are close to each other on the real axis, this does not guarantee their singularity in the analytical continued solution has close locations. And in the end, we use the exponential asymptotic analysis with AA approximation. So the AA approximation is introduced in this study, and this method is capable of capturing all the singularity, capturing singularities for all values of kappa very effectively. For example, for kappa equals 2, using AA approximation, we obtain the singularity, which is given by here. And it is very close to the singularity from the exact solution. And we obtain the amplitude by doing exponential asymptotic analysis. This is the approximated, and this is the exact. And although it captures the location of the singularity precisely, but to obtain a good approximation, we also need an exact good approximation of the value of the theta. And for exact solution, the value of theta is always pi over 2. And if we apply AA approximation, we can see as we increase, as kappa get in larger, the theta, the approximation for the theta improved. So essentially for smaller kappa, the prediction of the anti-resonance condition will not that precise, and this is our comparison for kappa equals 0.5. So as you can see, for kappa equals 0.5, actually the anti-resonance condition where the cancellation happened actually was not that precise. As kappa get larger, because as kappa get larger, the theta get closer to 1.5, then the agreement of the anti-resonance condition get better. So this is the comparison from the AA approximation method. And here is some open problems. First one is we want to, because the diatomic totalities with exact leading order solution was studied in this study. So we want to see whether we can pretend we don't know there is an exact solution. Can we solve this using an approximated leading order? This turns out a little bit tricky than the woodpile system, because for the woodpile system, the singulent equation is simpler. However, for the diatomic totalities, the singulent equation is this form. So when we applying the, because we applying the exponential asymptotics, we need to decide the strength of the singularity. And as a result, we need to look for the local behavior of the singulent equation. So when we apply the exact solution, we get the exponential of a logarithm. So actually the logarithm actually cancel with the exponential. So we can get a constant value. But if we pretend we don't know the exact solution, for any approximation method we applied, the leading order solution near the singularity is given by this form, and then the exponential of something that is large, we can't actually get a constant singularity strength. And also there is a comparison between Toda and Toda woodpile and the diatomic Toda. So first, if we look at the Toda woodpile, we can see for kappa equals 0.5 at the mass ratio 0.15, the cancellation happens. The Nanoptera becomes soliton. So can we say the mass ratio at 0.15 is spatial? Not really, because if we change our initial condition, then the mass ratio 0.15 is no longer spatial, because the anti-resonance condition shifts as we change our initial condition. While for the Toda lattice, if we change the initial condition, the location of the anti-resonance condition does not change. So we can say the mass ratio is spatial because it is the mass ratio at which all the Nanoptera becomes solitary wave. So it is also interesting to study physical process in diatomic Toda with spatial mass ratios. And this work is supported by Dr. Lustri's research grant. And that's all. Thank you for your attention.
Thanks, Guo. I'd like to invite any sort of discussion points on that. Phil, I think you're muted.
So I was actually talking to someone in the background. But,
oh, right.
Yeah, so this question of how to do the leading order problem is quite interesting. And, you know, it's the use of the tanh expansion is something I haven't seen before. And I guess you have this method where you either use tanh with a series expansion of the CN coefficients, or you have or you're using AAA, which is, I guess, I think of that as Pade, similar to Pade.
It actually differs in one pretty significant way, which is that sort of classical Pade gets all of it from in the same way as the tanh from a point, which means it can go a little bit wrong far away, whereas AAA spaces out the approximation, so it's gets the accuracy over a range, avoiding that very specific problem.
And then the third question, well, not third question, but the third point was you do have an intrinsic singularity structure of the leading order problem that you mentioned at the very end. And I guess there's this very complicated issue of how your CN coefficients, what are the convergence or divergence properties of that, because of the fact that you're imposing a different singularity structure than the actual problem, and similarly for AAA. I don't know what the best way of studying that problem is. I mean, this is the problem that I've asked of you and lots of people, which is you have a problem on the axis that you don't know what the singularity structure is, and you want to approximate it in different ways. So you can approximate it with your tanh function, or you can approximate with AAA, or you can approximate it with a Fourier decomposition, or et cetera. So there are many different ways. And what you eventually have done is you have your usual series in UN and Vn, and then now you also have a series in Cn, I guess, and also your AAA series. And it's not obvious at all how the convergence now hinges upon your other series. You introduce this new series in it. So, and that's not a question. It's just I'm not sure what.
Oh,
This
but
seems
I
like a
think
very important.
I think the Cn only in the leading order solution. So like yes, we have series in UMVM, but now we are focused on the leading order, so it's U naught V naught.
But the point is that the Cn, how many Cn's you keep will change how well you're approximating your solution off the axis, right? Which is
I was
Right.
going to ask why you chose 5.
5. Yeah.
Haha.
Why not 3 or 7?
Good question.
Okay, you can choose 3. Choose 3 is you can get less accurate result, but if you get the 7, it's negative. So maybe I showed in one slide, if you include the negative value, will force the agreement not well for.
Well, as long as the biggest one is positive, though, you could go to 9 then, right? Until you get a positive one.
With the
Yeah,
catch
but
that at
it's
that
not
point it
always-
stops being monotonic. Sorry, Guo.
Oh, why I think it's not always positive, so we have to stop when it is negative.
Why is this? What's this monotonic issue that I didn't catch that? Do you
When
need
you have
to-
a solitary wave, it shouldn't have sort of a trough and a peak in this kind of context. It really should be, it should go up and then level off. And if you have negative coefficients, you run the risk of getting a wave that goes like this, sort of down and then up. And
But
Run the
isn't
risk,
that-
but because they get it, it's not necessarily true that it'll do that, right?
maybe.
So I guess the question here is, if you do like a ratio test or you do some kind of convergence test on the Cn and you compare that with your eta and or alpha, the other critical parameter, I guess, is do you see that the convergence is doing something funny in any way? Can you take a limit? Can you take a different limit and show that your Cn stuff ends up doing funny stuff?
That's a good question, because for this one, clearly Cn can't keep going. I must stop at the certain specified.
Sen and Manciu conjecture that it's convergent. Whether that's true or not, I don't know. But this is one of those situations
Don't
where
think it's convergent, because you can't always guarantee it's positive. So essentially, I don't know.
the CNs do decay pretty fast, which is sort of an interesting observation that I don't know what it means.
Even in the limit that the singularities are converging.
I don't know.
Oh, if you have when you have negative value, if you see the singularity, it is not convergent. So say if you keep all the C1, C3, C5 or positive, then the singularity is convergent. So including more does not change the location of the singularity very much. But if you include the negative value, the singularity just stop jumping up, down. So yeah.
And do you
you-
have a way of solving the leading order problem without an approximation? Can you just, sorry, I mean, you're always doing an approximation, but can you solve it computationally without imposing a separate series approximation on it?
Oh yeah, you can always get a numerical value, but you need an explicit form to do exponential asymptotic analysis. So
In their approximation, they use their numerical value, right?
Yeah, I know.
Numerically, solve it on the real line, and then you're trying to work out what it's doing in the complex plane.
Yeah,
And the tangent is
yeah,
a guess, right?
yeah. So you're always doing a kind of a finite, you'll do a finite difference or some other approximation when you do it numerically, but the I guess the point is, the point is that what structure do you impose on that? What structure does that numerical approximation impose on the solution? As opposed to if you do it spectrally, so if you do it spectrally with a, some kind of decomposition, then you're imposing some structure. So you're contending with the convergence of that extra structure. And when you do it numerically with finite differences or some other scheme. So I haven't done these kind of discrete problems. I'm asking what what other ways do you have of solving for U naught?
I may not have really good ways. So because essentially precise solution is not available, and because the discrete problem, it always have a kink shape. So that's why people propose to use tanh to approximate.
But when you calculate your leading order, you set up a system and then shoot in a wave, right? And you tune the amplitude to, yeah, okay. What's the system you set up? Sorry, I realize I should probably know this.
So it's a monatomic chain. I excite with so I kick the chain with a velocity impulse, then it generates a solitary wave. Then, so.
But it's essentially a finite difference type scheme, right?
Oh, it's velocity valet.
That's right, symplectic.
I have another question, which I don't know if it's related, and that's that your approximate solution gets the wrong power out the front.
So, yes.
So is that because your leading order solution doesn't have the right singularity? And is that a way of saying actually your tanh thing is not working from that point of view? It's picking where the singularity is, but it's not getting the strength of the singularity right.
Yeah. So for woodpile, we don't know what is the exact solution is. So we don't know whether it gets the right power or not, because we don't know the exact
But for the
solution.
Toda, you are able to compare, right?
Sure.
It does impose a power. So the form of the ansatz imposes a specific power strength, which is one of the, I think, hiccups that we really all need to sort of work out how to deal with this. Because necessarily that gives you a certain amplitude, which kind of means when it's wrong, because the method should probably be robust in some way, it should capture things in a certain range, but you crank eta small enough and eventually everything's going to break. There's probably some kind of sensible hybrid method, which right near the singularity uses the local expansion and away from the singularity uses the numerical analytic continuation.
And AAA also got it wrong, right? It wasn't that your tanh
AAA,
AAA also get it wrong. Yeah. Although AAA
anything,
has the right location, but the strength is wrong.
So you might
John,
notice.
what is the thing that you're talking about in the final formula that shows it's wrong?
The amplitude of the exponential. So there's an e to the minus something, and that depends on the location of the singularity. But then there's the e to the -1 in front of the approximate solution, and there isn't in front of the exact solution.
Yes.
And that usually arises because your your approximate leading order solution didn't have the right power as it approaches the singularity.
Yes. No, it does not have.
And for the woodpile one, you don't know what power it is.
For the woodpile, you don't know what it is, but for the Toda one, you do know. So it was.
Yeah. Why is it so hard to figure out what the power is for the woodpile? Sorry, that's not. It's not a obvious. Is it particularly difficult, or I guess
could probably do some local balancing, right?
But is that tricky? That's different from the usual differential equation dominant balance stuff.
I don't know. That's worth finding out, to be fair. We really need to sit down and do that particular piece of analysis. We've been kind of saving it for the diatomic one because that's got a whole bunch of nasty problems that we didn't talk too much about. But yeah, so just sort of gluing in the local behavior near the singularity is probably the right approach there, because that's something that you can almost always calculate.
But then can you modify your tanh ansatz so that it's got the right singularity?
So that would be interesting.
I mean, maybe tanh is not the right.
But if it doesn't, it doesn't.
But there are other functions that look like tanh, right, that might have the right singularity.
Yeah.
I mean, worst case scenario, you can always take a sum of the right kind of strength singularity and treat that as a base approximation, some kind of rational approximation with a denominator that you know.
I mean, I think this is one of the big questions that we should all be asking, which is like outside. So the route that we're currently going through is we impose the function that you want to approximate the solution in the complex plane. So you say, I'm gonna write it as a tangent function with an unknown series of CNs, or I'm gonna write it through AAA. And yeah, we can look into our exponential asymptotics and figure out for that function, let's try to figure out what are the adjustments necessary because you're not using the right function or because it doesn't have the right power. But then someone else comes along and uses a different function, and now, you need a new theory. And so again, that's not a question. I just feel like,
Yeah.
I don't know what the best way of producing a theory for this issue is, which is in problems where you don't have an explicit form and you're using some kind of approximation, what can you say about the eventual exponential asymptotics? And can you do it in something more general than just one theory for AAA, one theory for PAD-A, one theory for these tangent functions?
You'd hope it would be more general than that. I think that any general method is probably going to break down into a few steps. The first step will be find where the singularities are any which way you can. The second step is going to be find their strength, find the local behavior near that singularity in sort of some kind of local expansion. And the third step will be numerical analytic continuation to fill the gaps, because AAA kind of doesn't give you the right answer in the very neighborhood of the singularity, nor do any of these methods, but it's pretty good away from it. So Guo mentioned the diatomic one, and you'll notice, so the singularity in woodpile, the reason we do woodpile is because it's basically cheating. The singularity is, the singulant is linear, which means the U0 doesn't appear in the singulant equation at all, other than where the singularities are, which makes it a bit more friendly, because if you know if that's all you need to know, these methods are very good. But the second you have U0 coming into the singularity, into the singulant equation, which is normal for any nonlinear type problem, you run into the fact that if your U0 breaks down an important part of the expression, then you lose accuracy pretty badly. So I think any systematic way has to hit those 3 points: singularity location, local singularity behavior, analytic continuation away from it.
How do you modify the equation so it's nonlinear then? So to have that U0 appearing in the singulant?
Modify
the woodpile problem. The woodpile problem. What is the singulant for that one as a function of U0? Is it just chi prime equal to
written down, Guo?
So is chi prime equal some constant for woodpile?
Yeah. Like
for the diatomic,
right?
is chi prime equals some exponential to the U0.
Yeah, woodpile's a nice little test ground, but as soon as the singulant equation starts to include more complicated things, there's a concern there. But I don't know, I feel like we have all the ingredients for getting the method right. We're just kind of playing with it to try and make it work.
And have you done, and is there a reason why you chose AAA, and then Trefethen has nice AAA stuff?
Because I got thinking about it when he was talking once, and I was like, we have PAD-A as well, sort of classical PAD-A.
And so you can
use
PAD-A.
Actually PAD-A is, we has the result of PAD-A. The reason the PAD-A is, it also gets the right position of the singularity, but the PAD-A requires the calculation of the 16th derivative to get it right. For TODA, like you have the exact solution, compute the 16th derivative, just let Mathematica do. Suppose if you don't have exact leading order solution, taking 16th derivative of a numerical solution can be a pain, because each time you get some error of the 16 times, you're gonna. Because for PAD-A, essentially to get the 8th term, you have 16 derivative. So that's
I mean, ideally, you want something that you can extend to arbitrary precision, right? Like that's a pretty key ingredient is if you can make your numerical solution as precise as you want, you'd like the rest of the method not to let that down. Which is where these very low, like using all of the information at one point to work it out causes problems. But I don't know, it feels like you could combine them as well, right? Because tanh is just a functional form, throw a rational function in there and things probably look okay.
Yeah.
The other catch, by the way, is if you have a branch cut, so we didn't sort of mention this, but it's something we're aware of in the background, is you get an accumulation of singularities, which, you know, you can kind of close your eyes and treat as separate, but as you well know, when they run into each other's inner regions, you probably have to start thinking about that more carefully too.
Yeah, I'm quite curious about someone writing a paper on the recombination of the branch points in the Pade approximant. So there's the stuff by what's his name from Ohio, Baker, right? So there's that, he has that book on Pade approximants and so forth, and there's a computation you can do to resum the branch points of a Pade approximant. So, you know, your Pade, instead of a branch point, it's imposed a series of poles. And so you can do this calculation that says, okay, all the poles add up to a branch point.
Yeah.
And so I guess it would be nice to do your exponential asymptotics on that toy problem. So just see how that calculation, that recombination calculation works when you are trying to do exponential asymptotics for each of the singularities.
That would be interesting.
I guess that's the simplest problem you can try doing.
Yeah, that's a good idea. Another worthwhile sort of line to take is if we understand how those singularities accumulate, then can we see an accumulation of singularities and go, oh, that's a 5/2 branch cut. But every way I've tried to do that has just become so sensitive that it's quite tricky to get it to work. Because I've been playing around with that idea to see if you can't reverse engineer it, but that's hard.
Well, the
also,
way
weirdly, and sort of, go on, Phil.
The way they usually figure out what the power is, I guess you take a contour integral around the point, right? And you write your integrand in some fashion, you take a contour integral, you calculate that. And if you write it in the right way, you'll get 5/2 or some function of the power. So maybe if for Pade, if you integrate around the branch cut, it's the same idea that if you integrate around the branch cut and you write things in the right way, you'll get 5/2 or something. So that's the way to do it. I have seen people do that. I have seen people calculate stuff with Pade to high accuracy and then try to add things up and figure out what the power has to be. But I don't know how, whether it's it's practical enough.
Worth following up on though, Guo. I think we should probably write that one down. Yeah.
And have you done AAA on the woodpile one? I can't.
Not yet.
Not yet.
That's the next thing to do.
There's another fun application that we're going to jump onto at some point. There's a few experimentalists, including Mason, who did magnetic beads with longer range interactions, and they showed it has solitary waves, and we're going to play with that because why not? But again, you could never hope to write down the leading order. So this is where it all comes back to every time is if you can't do the leading order, what is your best option?
The other question I had was about your alpha. The linear solution has an alpha -1. So is there some kind of distinguished limit with alpha tending to 1 or 1.5 or something like that?
Also, yeah, alpha equals 1 is the linear case. Linear case has no solitary wave. And for alpha smaller than 1 is also, there is no solitary wave. If you want oscillatory wave, there is proof you need a super quadratic. So that's why alpha should be greater than 1.
So it'd be interesting to do alpha being like 1 plus epsilon.
Because you can see that in your eta versus amplitude graphs that it was progressively getting worse as alpha gets smaller.
Yeah. So it might be, I think you're exact. I think that sounds pretty, because there is some phenomenology there that we haven't been able to explain, and a distinguished limit actually makes a lot of sense. So the idea, Guo, of a distinguished limit is you've got 2 small parameters and the order which you take them is very important.
True. I think for the woodpile no precompression, we only have 1 parameter.
No, but we can introduce another one. We could say 1 plus epsilon and make the power pretty close, so being very close to linear. And then there would be a second small parameter, which would be a measure of how close to linear we are.
And alpha didn't appear in the singulant in the exponential arc. It just appears in the for the linear case, or the I was just okay. Can you guess what the distinguished limit has to be? 1 plus epsilon to something.
I mean, I hadn't thought about it till you said it. So, does in the exponentially small terms, does alpha appear? Alpha appears, right? Alpha definitely appears.
Actually, alpha appears in the velocity, so it does not appear explicitly, but it appears in the velocity. So the velocity is in the denominator, and the velocity is to the power of some alpha, something like that.
What does the velocity do? Can we specify that in this problem, or is this one where it's specified?
So velocity for each alpha is different. So
Yeah,
for
that's
each
right. And I guess the velocity as alpha goes to 1 is some kind of speed of sound type situation.
Yeah.
I guess the finite domain problem is also quite interesting.
Yeah,
I mean, the experiment you showed was on a finite domain, and suddenly it became infinite.
The Newton's cradle.
Oh yeah. So it's periodic.
We can simulate finite domains, but I haven't done any sort of maths on that at any point. I mean, the experimentalists consider it, so it seems like a nice one to do just to validate against experiment. They normally run it slightly differently in that they start with a specific impulse, whereas we start with, a solitary wave has settled in, which is obviously a slightly different situation. It'd be kind of interesting to, I mean, it would be legitimately interesting just to do an impulse, get some actual numbers and compare them against an actual physical setup. Because the reason they study this is because it's so easy to set up in a lab.
And have you seen an extension of this to 2D? Nanoptera.
It would be interesting. It's an idea I've played with. We have a PhD student, Aaron, who's doing sort of lattice 2D lattice equations, which we treat as discretized. Because you'll notice we essentially treat this as continuous. This is an infinite dimensional system, which Peter Miller once took me to task over, asking how many of the ideas from Chapman, King, and Adams extend naturally to an infinite dimensional system of equations, to which I shrugged.
Well, I was going to ask how Chapman and King discrete stuff relates to this.
So it doesn't. This is essentially distinct from that. But we do discrete, that kind of discrete stuff on lattice equations just to kind of see how that works. We've been playing around with that. The answer is, it's complicated. Of course it is, but it's interesting.
But is the point that instead of the second derivative, you discretize that, and then is that the discrete is that?
Yeah, so that's what you would do. You would essentially
discretize
discretize time as well. And that's got some interesting stuff, but it's kind of orthogonal to this. Just because only so many things you can do. But the impulsive start would be interesting, and you'd see the same stuff, right? Because the impulsive start is not a, it's going to have transient effects, which will be higher order Stokes phenomenon and all of that.
Yeah, so I'm interested in the 2D problem, but you don't have a traveling frame anymore in the 2D problem, so
No,
that's,
which is
so
fine.
I'm
There's nothing intrinsic
curious.
to the traveling frame.
I guess I'm asking. I have a 2D. You extend your formulation to 2D, and you don't have your traveling frame anymore. Do you have experiments or numerics showing that would be experiments with these exponentially small effects?
I haven't delved into them. The paper with experiments on that only came out a couple months ago, and my plate's been a little full. But there's an interesting thing as well, which is if you're going to arrange it in a lattice, do you want it to be a square lattice? It seems more natural to be a honeycomb lattice, which would be kind of interesting. And there's some interesting, I think Hardy Sasanto did some stuff on that at some point, which I need to dig up on. But yeah, I think we should all talk more about sort of the lattice type stuff at some point. Well, we should always all talk more about a lot of things, but it is what it is.
I'd be curious to your AAA on 2D domain.
Is that a thing you can do?
I don't know. I mean, I guess a lot of this is dependent on complex analysis. So I don't know how that works, but I guess that's a very interesting, or pod A on 2-dimensional domains, I guess.
You're a brave man. No, pod A should work, right? I mean, I would think.
Yeah, but if pod A approximates a branch point with a series of poles,
oh yeah,
I don't know what that does for a 2-dimensional function on the real axis.
That might be worth looking up, because that would be very strange. Yeah, I'm
Anyways,
not sure.
I have to run, but
Yeah.
Thank you to you and Guo for a very nice talk. We'll have to catch up.
Maybe we'll call it a day for the discussion there. And thank you very much, Guo. That was really great. I very much enjoyed it. Thank you everyone who participated in the discussion and everyone who hung around. That was really helpful and gave us, I think, both a lot to think about. All right.
Thanks, guys. That was good. I'll go look up those papers now.